Okay guys, in this video we're going to be talking about what are called integrated rate laws. So integrated rate laws can be derived from the rate laws that we were working with previously, and they can be used to calculate the concentration of a reactant or product at some point in time. And so they allow you to understand, and we'll be doing some graphical analysis of this, how the concentration of a reactant or product changes with time. So integrating the rate law allows you to do that. And then there's an assortment of calculations we can do for different types of kinetics. We're going to focus on zeroth-order kinetics, first-order kinetics, and second-order kinetics. As I said, there's going to be a graphical component to these that we'll look at. There's something called the half-life, which we'll need to be able to calculate for each of these types of kinetics. And then this part here, this is related to the graphical, determining the reaction order from concentration versus time data and graphs. So let's get into this. So as we've been discussing, the concentration of a reactant and a product changes with time. And the integrated rate law describes how that concentration does depend on time using a mathematical function. So for each of these kinetics that we see here, we are going to be looking at the integrated rate laws. And here's the generic reaction that we're going to consider. So some reactant falling apart into products, we're going to look at first-order kinetics, second-order kinetics, and zeroth-order kinetics. So it looks like we're going to start with first-order kinetics. As we go through these different types of kinetics, you need to know the following information. You need to know the differential rate law that we've worked with previously. You need to know the integrated rate law. You need to know the graphical components that go along with the integrated rate law. You're going to need to know the units of the rate constant, and you're going to need to know the half-life for that particular reaction. I don't know if I mentioned half-life there twice or not. Can't remember. Anyway, let's start with first-order kinetics. So the hallmark of first-order kinetics is that the concentration of the reactant decreases exponentially with time. Okay? So here is the generic reaction. Its form doesn't really matter. We just know that it's a first-order reaction. So from the rate, like this is what we've studied previously. We studied this on the first lecture of this chapter. You can express the rate as minus 1 over the stoichiometric coefficient times the change in the concentration over the change in time. Now previously we were working with the average rates. So we were doing expressions like this. Well, if you just make the time interval smaller and smaller and smaller until it's infinitesimally small, then it becomes an instantaneous rate. And so that's what the D notation means. It's from calculus. It means infinitesimally small. So this is the what I often call the left-hand side of the differential rate law. And then what we learned about in the last video, reaction rates, rate laws. The fact that it's first order tells us that the rate is proportional to the reactant concentration raised to the power of 1. That's what first order kinetics means. And so I call this typically the right-hand side of the differential rate law. So this is the differential rate law. It has the left side and the right-hand side, and we know we've studied what these things mean. This rate law can be integrated to give the integrated first order rate law. Okay, and you see that it has this exponential dependence. And so we've got the concentration of the reactant is a function of time. This is the initial concentration of the reactant at time t equals 0. And then this is that exponential decay that I'm talking about, exponentially decreasing. You see the rate constant right here. It's a minus sign and the time. I'm going to go ahead and plot the graph of it myself here. So here's the graphic that goes along with the exponential function, the exponential integrated rate law. So we've got our reactant concentration in units of moles per liter. This would be the initial concentration at time t equals 0. We've got time going this way, say in units of seconds. The exponential decay is going to be something that does this. Just decreases like that. Okay, so that's the graphical component to it. We can rearrange this equation. So the exponential equation, you can take the natural log of both sides. I'll go ahead and show you how it works. Take the natural log of both sides. So natural log here, natural log there. We have natural log of a product, so we can write it as the natural log of the sum of, we can write it as the sum of natural logs. The natural log brings down the power from the exponential, and so we wind up with this expression here, which you can rearrange one more time. Well, no, we have it right here. That's exactly what I want, that expression. Okay, I call this the linear form of the first order integrated rate law. And the reason I do that is because if you plot this along the y-axis and you plot time along the x-axis, minus k is some slope m, and then the natural log of the initial concentration of the reactant is some constant b. What you have is the equation for a line. And so the other graphic that goes along with first order kinetics is the natural log of natural log of A as a function of time. Here we would have the natural log of A0, and it would be a decreasing function where the slope is equal to minus the rate constant. So the nice thing about these integrated rate laws is that you could measure the concentration versus time data, right? So you would measure concentration at different time intervals, and then you would plot the natural log of that data versus time, fit it to a straight line, and then the slope of the line, using Excel or Mathematica or some software to do the linear regression analysis. The slope is equal to minus the rate constant, and the intercept is equal to the natural log of the initial concentration. And so you can use this approach to find rate constants. Incidentally, if you were to compare two different reactions with two different first order reactions with different rate constants, let's say this would be the fast one, so this would have a large value of the rate constant. Here would be the curve for a reaction that had a smaller value of the rate constant. Okay, it would decay more slowly. Okay, so the value of the rate constant is very important in determining how quickly the concentration decreases. The larger the rate constant, the faster the decay. So this would be a medium-sized rate constant. Here would be a really large rate constant, and larger still. So as you go this direction, K increases. And you would have increasing slopes in the linear plot. I don't want to leave out the units of the rate constant because that's often an exam problem. How do you determine the units of the rate constant? Well, you determine them. You can either memorize them or you can determine them from the rate law. So the units of rate are always moles per liter per second, or at least these are always a viable unit. Concentration always has units of moles per liter, and so you can use this to algebraically find the units of the rate constant. You see the moles per liter are going to cancel out, and so the units of the rate constant are 1/seconds in this case. The units of the rate constant will vary depending upon the order of the reaction, as we'll see when we look at the second order kinetics. But first, I think we have a problem to do. So here, the rate constant for a first order decomposition reaction of cyclobutane at 500 degrees Celsius is 9.2 times 10 to the minus 3 reciprocal seconds. How long will it take for 80% of the sample to decompose? Okay, so the first order integrated rate law for this will be concentration at some time t, initial concentration at time 0, exponent minus k times t. So they want us to tell them how long, what is the time it takes for 80% of the sample to decompose. Well, how much of the sample do I have left if 80% of the sample has decomposed? The answer is 20%. Right? So what they're telling us is that C4, the concentration of C4H8 at this time is going to be equal to 0.2 times the initial concentration. That's what this statement means. And you have to read it carefully because there's different ways they can word this stuff, and that changes how you calculate it. But anyway, they say 80% of the sample has decomposed. That means you've got 20% left. And so if we plug this in, what you can see is that the initial concentration is going to cancel out. We don't actually need it. So we're going to wind up with 0.2 equals e to the minus kt. To get the time out, we take the natural log of both sides, solve for the t divided by k. K is 9.2 times 10 to the minus 3, 1 over seconds. I'm getting 175 seconds for this. So this is one application of the integrated rate law. You can calculate the time it takes to reach a certain concentration, or given the time and the rate constant, you can figure out, how much will I have at a particular time. Let's see. Oh, this is kind of fun. Radioactive decay. Radioactive decay, I believe, is almost always first-order kinetics. So here we've got some iodine-131 that's radioactive, and it's used as a medical treatment for thyroid cancer. Here's the reaction that we have. So this is a nuclear decay reaction. First-order kinetics, the decay constant, so the rate constant is 0.138 reciprocal days. How many days will it take for 90% of the iodine-131 in a 0.5 moles per liter solution to decay to xenon? So if 90% has decayed, then 10% remains. So the iodine-131 concentration at this time that they're interested in is 0.1 times the initial 131 concentration. And that is equal to the initial 131 concentration, e to the minus kt. So the initial concentrations cancel out. We take the natural log of both sides, solve for the time. I'll put the minus sign there, k there. Take 0.1 times the natural log, take the minus sign, divided by this rate constant of 0.138 reciprocal days, and it gives me 16.7 days. Okay, so that's the first order kinetics. That's kind of a fun problem. Here's the graphical analysis. I'm not going to actually work the problem, but what they want you to do is to determine the rate constant for this I'll go ahead and do it. It's not that bad. So here we've got time data. concentration of hydrogen peroxide. So we've got hydrogen peroxide. It is decomposing to water and oxygen gas. And I think we need a 2 there and a 2 there. All right, so that's the decomposition reaction that we have. And so what they've done is they've plotted, or they've collected, the hydrogen peroxide concentration at different times. Okay, and now they are trying to figure out, they know that it's first order, so they plot their natural log of peroxide versus time graph, and they're trying to figure out what is the slope. Okay, so you can use linear regression to get the slope, or since you already know it's linear, you can use any 2 points along this straight line to calculate the rate constant. So we know that the slope of the line, which is going to be the difference in the rise, or it's going to be the rise over the run. So let's just take the first 2 points, and we're going to take natural log of the H2O2 concentration at time 2 minus the natural log of the H2O2 concentration at time 1 divided by time 2 minus time 1. The slope is going to be equal to minus the rate constant. Okay, and so we're solving for the rate constant. So 0.5 natural log of let's see. Well, they've already calculated the natural logs for us in this third column. So I'm just going to put minus 0.693 minus 0 divided by 6 minus 0. And this is units of hours. That's equal to minus k. So we've got 0.693 divided by 6. Correct the minus signs, and you get k equals 0.1. I'm just going to call it 2 reciprocal hours. For this problem, they're asking us to take a look at the data and say, hey, is this a first order reaction or not? And so they've plotted, they've measured concentration versus time, and then what they're doing is they're plotting the natural log of that concentration versus time. And we look at the curve and we see it's not a straight line, therefore it doesn't match first order behavior. So this is definitely not a first order reaction, because this graph should be linear, and it's not. All right, well, we'll move on to the next type of kinetics, and then eventually we're going to come back and do half-life for all of the kinetics. So for second order kinetics, it's the same generic reaction that we're considering, but this time the reaction, we're told, is second order. So here's the differential rate law for that. It can be integrated to give you the integrated rate law that looks like this. So 1 over A equals 1 over A0 plus KT. Actually, we could rearrange this a little bit. Here you see I've made a manipulation, and then now we can take the reciprocal. And so if you want, not that you need to, I would prefer to put the K, then the A0, then the T, right? Because that's the independent variable. So this is the concentration versus time function, okay, for second order kinetics. The equation that we have written here is nice because it is in a linear form, as I'll illustrate next. So if we plot 1 over A along the y-axis, and we'll let t be our x, and plus k can be our slope, and 1 over A0, the initial concentration, can be our intercept, we have the equation for a straight line. So when you plot second order kinetics data, if you plot 1 over A, which starts at 1 over A0 and goes up, the slope is equal to plus the rate constant. So you can measure the concentration versus time data and plot it in this fashion, do a linear fit, and then the slope gives you the rate constant. The units of the rate constant, again, I just want to illustrate this because it's a very common problem on exams. What are the units for the rate constant for second order kinetics? Well, the rate always has units of moles per liter per second. Doesn't matter what type of kinetics you're considering. The units of concentration, moles per liter squared. These will cancel one of those. And so then K is liters over moles seconds. You can do this for any type of rate law you want to find the units of K. In this problem, what do we have here? We've got a reaction of butadiene gas. The reaction is second order with a rate constant of 5.76 times 10 to the minus 2 liters per mole per minute. Under certain conditions, if the initial concentration of butadiene is 0.2 moles per liter, what is the concentration remaining after 10 minutes? So this would be an example of using the integrated rate law. And so I'm going to write that down. We can do it in different ways. I would suggest if you're only going to memorize one of those equations that I showed you, I would do this one. It's definitely the more important one. Now, we know the initial concentration. We know the rate constant K. And we know the time, 10 minutes. They want us to calculate this value. And so what we'll do is we'll just plug in the numbers as we have them. Plus the rate constant. Take that times the time of 10 minutes. So I'm getting 5.576. This is going to have units of liters per mole. Then we take the reciprocal of both sides. You get 0.179 moles per liter. So the concentration drops after 10 minutes from 0.2 moles per liter to 0.179 moles per liter. So it illustrates the use of the second order rate law. This is the same type of problem, same reaction. Here they're changing it around a little bit, so it's 0.02 is the initial concentration, and then 20 minutes, but it's solved in the exact same way. You just plug in different numbers. So I'll leave that as an exercise for you guys. Let's look at some of the graphics. Test the data to show whether the dimerization of C4H6 is first order or second order reaction. So what you've got here is you've got your time, and you've got the measured concentration. You can calculate the natural log of the concentration, and you can plot the reciprocal of the concentration. So when you plot the natural log versus time data, okay, if it were first order, you'd get a linear graph. But this is not a linear graph, so it's not first order. For second order kinetics, when you plot the reciprocal of the concentration versus time, it should be linear and upwardly increasing, which it is, therefore it's second order. Okay, so you can use a graphical analysis to identify the reaction order for a reaction. What about this graphic? So just like we would expect, if you plot 1 over the concentration versus time, we get an upwardly increasing graph. Therefore, this should be a second order reaction. All right, the last type of kinetics, the zeroth order kinetics. The hallmark of zeroth order kinetics is that the reaction rate is constant and the reactant concentration decreases linearly with time. So here for that generic reaction, we have our differential rate law, and we're told that it's zeroth order. So the rate equals the rate constant. Since rate has units of moles per liter per second, so does the rate constant, moles per liter per second. When you integrate this rate law, the equation you get is already in a linear form. Okay, so I'm going to go ahead and draw that. So for zeroth order kinetics, when you plot the concentration versus time data, okay, you'll start with the initial concentration. And what's going to happen is it's going to decrease linearly until you run out of reactant. Okay, now you've gotten down to 0 reactant. There's no reactant left, and so the reaction stops. The slope is equal to minus k. Let me illustrate. A equals A0 minus kt. Right, you plot this along the y-axis. T is your x-axis, minus k is your slope. This will be your intercept. And so again, you got the equation for a line. So for zeroth order kinetics, you plot concentration versus time. If you get a linearly decreasing graph, you know it's zeroth order. And then the slope is equal to minus the rate constant. Oh, here's an example of that. Decomposition of ammonia on a hot tungsten surface is found to be zeroth order. Okay, so here's the rate law. This is the integrated rate law. If you plot concentration versus time data for decomposition on the tungsten surface, you find that it's linear, which means that it's zeroth order. However, if you try to do the same reaction on a silicon dioxide surface, you get an exponential curve, which means that it's first order on the silicon dioxide surface. So the experimental conditions, they make a difference in the kinetics. You know, it's the same decomposition reaction, but a different catalyst. And so that changes the mechanism, as does the experimental conditions, or at least it can for certain reactions. All right, so that's zeroth order kinetics. The next topic is half-life. And so the definition of half-life is it's the time, so it's a specific time at which the concentration of the reactant has decreased to 1/2 its initial value. Okay, so this is the half-life condition. And for the different types of kinetics, you get different formula for the half-life. So if I take the first order integrated rate law, and if I plug in the half-life condition, so at the half-life time, the concentration of the reactant equals 1/2 its initial value. We see that those cancel. We'll have the natural log of 1/2 equals minus kt 1/2. We'll rearrange it, make use of some rules of the logarithms, and we get this expression here, okay, which is what you see on the screen. And I want to point out a very important feature, and that is that the half-life time for first-order kinetics does not depend upon the initial concentration of the reactant. Okay? It is, however, inversely proportional to the rate constant. So the larger the rate constant, the smaller the half-life time, the faster the reaction goes. Let me illustrate the half-life using a graph. So for first-order kinetics, if you plot the concentration, here's its initial concentration, you get this exponential decay. So let's call this, 100%. Here's 50%. How long did it take to go from 100% down to 50%? That's our half-life time. How long does it take to go from 50% down to 25%? If I've drawn the graph correctly, and I kind of did, the half-life interval is the same as the first one. So the two time intervals are the same. And then you can repeat it. Okay, so here we went from 50 to 25, go to 12.5. For exponential decay, the half-life interval is always the same, and it's the same forever. Okay, so this time interval is supposed to be the same as that one, and the next one, and the next one, and the next one, and so on. The half-life time doesn't depend upon the starting concentration. Now, if we consider second-order kinetics, here is the integrated rate law. Plug in the half-life condition. At the half-life time, the concentration equals half the initial concentration. So we can rearrange things. 2 to the 1/2 equals, let's see, that's going to give us 1. It gives us this expression. And so we see that the half-life time, again, is inversely proportional to the rate constant. The larger the rate constant, the smaller the half-life time. That makes sense. The faster the reaction goes. However, in this case, the half-life time depends upon the initial concentration. The larger the initial concentration, the smaller the half-life time. But as the reaction goes on and on, the concentration that you could imagine starting with decreases. And so the half-life time gets longer and longer. So that's kind of one of the features of second-order kinetics, is that compared to first-order kinetics, they sort of drag out. They sort of lag along. They get slower and slower compared to the first-order kinetics. For the zeroth-order kinetics, right, when you've got this expression, it should be minus kT. Okay, plug in the half-life condition, rearrange, you get this. Again, inversely proportional to the rate constant. So the bigger the rate constant, the faster the reaction. However, here the half-life time is directly proportional to the initial concentration. So the more you have, the longer the half-life time. But as the reaction goes on and on, the initial concentration that you can imagine starting with decreases, and so the half-life gets shorter and shorter. Let me illustrate. So we'll go back to that zeroth order graph. Here's time. Decreases like that. Okay, so what's the first half-life time? So here's 100%. Here's 50%. Here's the first half-life interval. Fairly long, okay? Now let's do it again. So go from 50% down to 20%, 25%. We see that the half-life interval has now decreased, right? Because this is now our initial concentration. And so to go to half of that, the half-life, the time is shorter. And it shortens again and again. And you see that it goes down to 0 eventually, right? This is where the reaction, the zeroth order reaction ends. Some problems involving half-life. Calculate the rate constant for the first order decomposition of the hydrogen peroxide in water. The half-life for the reaction is 6 hours. So you can either memorize or learn how to derive the half-life formula. So for first order kinetics, the half-life is the natural log of 2 over the rate constant. They want us to find the rate constant. K will be equal to natural log of 2 divided by the half-life time, 6 hours. So we'll take 2 natural log divided by 6. That gives us 0.1, we'll call it 1/6 reciprocal hours. half-life time in radioactive reactions. So here it's the same formula. They give us the rate constant, and they want us to calculate the half-life time. So this is using this equation, natural log over 2 divided by 0.138. And I forgot the units. This would be reciprocal days, 5.0 days. So if you had a kilogram of iodine 131 in 5 days, you would have half a kilogram. That's how that works. All right. Well, that's you can work similar problems to the ones that I've just done for zeroth order and first order kinetics. They just use different formulas, so be aware of those and look for them in the homework. With that, I'm going to go ahead and stop this video, and we'll pick up with collision theory in the next one.